Hello everyone, welcome to Sam Science View channel. In today's video, we are going to listen to a science fact. What are the physics behind bouncing balls? Before getting into the video, please watch this entire video, and if you have any science related doubts, you can get it clarified through this channel. Now let's get into the video. Studying the mechanics of bouncing balls is a great way to learn simple physics. We can all look back on our childhood memories and find in some form or fashion a bouncing ball. Whether it be shooting hoops with friends or tossing a tennis ball against a wall while we were grounded, we have all played with these bouncing toys. While to most people, balls are rather unassuming objects, they actually serve as an interesting springboard into learning about many interesting physics phenomena: acceleration, velocity, energy. You can learn it all when you start looking at the physics behind bouncing balls. In any ball bounce, there are essentially seven stages that the action can be broken into during its motion, before, during, and after impact is examined. Let's break down the physics of bouncing balls. To begin with, we will look at the simplified seven stages of a ball bounce, ignoring any outside force other than gravity. We will break down each step in detail below with equations. Stage 1 is falling. This stage 1 is the beginning of every ball bounce, where potential energy from the height of the ball is converted into kinetic energy through acceleration due to gravity. In a simplified case, the ball falls in line with the force of gravity, which always points directly downward. On Earth, this acceleration due to gravity is measured as 9.8 meter per second square. This means, in essence, that for every second for falling, the ball's velocity will accelerate by 9.8 meter per second. Now, stage 2 is initial contact. The initial contact phase is just that, when the ball just barely makes contact with the ground surface. It will continue to fall under the influence of gravitational acceleration, but now a normal force from the ground surface opposing the force due to gravity will act on the ball. Now, stage 3 is deceleration or negative acceleration. After the initial contact, the ball rapidly decelerates, or rather accelerates, in a negative direction. The velocity of the ball still points downward as it deforms, but acceleration on the ball is beginning to point back upward as the forces from the reaction overcome gravity. This all means that the ball is pushing on the ground with a force greater than its own weight. So, acceleration must point upward. Stage 4 is maximum deformation. Following the deceleration stage, the ball has reached maximum deformation. At this point, the velocity is zero and the acceleration vector points upward. This is the lowest point of the ball as well as its maximum deformed point. If we assume the ball to be totally elastic and ignore other energy losses like sound and heat, then the ball would bounce back up to its original drop height after this point. You can see this in this picture. Stage 5, initial rebound. This stage begins the ball's journey back to where it began. Its velocity and acceleration vectors are pointing the same direction, meaning upward movement. the ball is less deformed than the maximum deformation stage, and due to its elasticity, it is now pushing against the surface with a force greater than its own weight. This is what will cause the ball to bounce upward. Stage 6 is zero contact rebound. At zero contact rebound, the ball is no longer deformed and is barely touching the surface, essentially only at one point. Velocity is moving the ball upward, but at this point, acceleration switches to oppose the velocity vector. This is because there is no longer any force from the elasticity of the ball pushing on the surface, giving it an upward acceleration. Acceleration due to gravity, which pulls downward, will now be the only force acting on the ball in a perfect system. Stage 7 is full rebound. At full rebound, the ball has left the surface and its velocity vector still points upward, though shrinking steadily due to the acceleration or deceleration due to gravity. Following the step, the ball will reach peak at a new step, one where its velocity vector is zero and the only force acting on it is gravity. Added variables and special cases in bouncing ball physics is a thing. The case of bouncing ball above was simplified to remove any other forces like air resistance, imperfect elasticity, spin, friction, and the force from an initial throw, among others. All this means that bouncing ball physics gets more complicated from here. When balls have any spin, as they usually do when thrown, and when the surface they hit isn't frictionless, the spin of the ball reverses from before to after impact. This is due to the force of friction. Assuming two dimensions for theory's sake, as the ball impacts with the spin in one direction, the friction force counteracts the spin of the ball, or rather, the friction force is always opposite to the direction of the slip velocity between the spinning ball and the surface. Since the friction force is opposite of the ball spin, it torques the ball in the other direction. It also causes the path of the ball's bounce to skew in the direction of the friction force. In simplified terms, when a ball spins in one direction, when it hits a wall, the friction between the ball and the wall overcomes the spin so much that it reverses its spin direction. This spin reversal doesn't happen if the ball and the wall's coefficient of friction aren't high enough. The coefficient of friction varies by material and surface and is essentially a number that indicates how grippy a surface or material is. In real life, non ideal scenarios, bouncing balls lose energy and eventually come to a stop. This is all due to the forces we ignored in the first example. When a ball hits a wall or surface, it makes a noise, which is a loss of energy from the ball's bounce. It also will generate some amount of heat, another loss of energy. Friction from the wall will cause energy loss as well as air resistance while the ball travels. In essence, the ball will never have as much potential or kinetic energy as it had from right after it was thrown or right before it strikes the surface, depending on the scenario. So, what we can conclude is that when you bounce a ball, you can learn about the acceleration, velocity, and what are the energy loss taking place in a bouncing ball. Whatever may be the weight of the ball, it is all happening due to the acceleration due to gravity. It is being pulled downward, and then due to the opposing force, it is being bouncing back to our cells, and it is reaching to a point and it is staying there. And if that has been come to a 0 point, it is being pulled back down. So likewise it is being bounced. So that's it for today's video. I hope so you got some idea about what is the physics behind the bouncing balls. And if you have any science related doubts, you can get it clarified through this Science Facts Treasury series. We'll meet in the next video with the next science facts. Until then, it's goodbye from Sam. Take care.